Today we're going to begin deriving the unit circle. But before we can get started, we have to review something from geometry, which is known as special right triangles. So there's two specific special right triangles which relate to the unit circle. The first one is on the left, which is our 30, 60, 90 triangle. And the second one is on the right, which is our 45, 45, 90 right triangle. The reason why these are special is because they have the same side length ratios no matter what. For the 30, 60, 90 triangle, the side facing 30 degrees is always equal to x. The side facing 60 degrees is always equal to x times the square root of 3. And the side facing the 90-degree angle is always equal to 2x. Now for our 45, 45, 90 triangle, both sides that are facing the 45-degree angles is equal to x, and the side facing the 90-degree angle is equal to x times the square root of 2. So to make our life easier, x is just going to equal 1 for all of these triangles. So now that simplifies all of our side lengths. So I went ahead and dropped the x here, replaced this x with just the number 1, dropped the x here, and replaced both of these x's with the number 1, and then also dropped this x. So we're almost done with creating the special right triangles that we need for the unit circle, but there's one last adjustment that we need to make. The hypotenuse for both of these special right triangles has to equal 1. So the easiest way to do that is if I divide all side lengths over here by 2, and if I divide all side lengths here by the square root of 2. So now I'm going to go through and I'm going to simplify all the side lengths, and I'm also going to rationalize the side lengths to get the square root out of the denominator. So now, as you can see, both of our special right triangles have a hypotenuse of 1, which is exactly what we want. And now I've also cleaned up the side lengths so that they're completely simplified and rationalized. So these are going to be the special right triangles that we use over and over again as we derive the unit circle. So here is one of the angles that you will be responsible for doing on your packet. Before I get started, there's just one quick note I want to make. In each of the quadrants of the unit circle, there's 3 little markings on your unit circle. These markings are here to help you divide up that quadrant. So the first mark is always made 30 degrees from the x-axis. The second mark is always made 45 degrees from the x-axis. And the third mark is always made at 60 degrees from the x-axis. So first things first, we have to draw our angle onto the unit circle. Remember, angles always start on the positive side of the x-axis, and then the terminal side is going to end in the counterclockwise direction wherever you are located. So in this situation, we got to remember that the first quadrant is 90 degrees. The second quadrant is going to go from 90 degrees to 180 degrees. And then the third quadrant is going to go from 180 degrees to 270 degrees. So we know we're located somewhere over here. So if this ends at 180 degrees and I want to get to 225 degrees, I know the difference between these two is 45 degrees. So according to these 3 markings, my angle is going to terminate at the second marking, because the second marking is 45 degrees from the x-axis, and 180 degrees plus 45 degrees gives me 225 degrees. So now the next thing that we need to do is we need to draw our special right triangle. So if I try to draw a triangle with a 225 degrees, we know that that's not possible because a triangle is a total of 180 degrees. So to get your special right triangle, you have to use the x-axis that's closest to the terminal side of your angle. So there's always the positive side of the x-axis and the negative side of the x-axis. Here is the terminal side of my angle, so the closest to x-axis is going to be the negative side. So I've went ahead and I've drawn my right triangle, my special right triangle, and there's a couple of things that I want to point out. I know I have a right angle located in the top left corner. I also know I have a hypotenuse of 1, and the angle that I'm interested in by the origin is equal to 45 degrees. So I can take this right triangle and I can redraw it much larger so that I can then analyze what the different side lengths are telling me. So out to the side, I went ahead and redrew my special right triangle. And again, I have a 90-degree angle. The angle that I'm interested is always the angle that's made with the origin, which is a 45-degree angle. The x-axis forms one side of my right triangle, and then the terminal side of my angle always gives me my hypotenuse. So again, here I have a 45, 45, 90 right triangle, so I should be using the ratios that we found on the previous slide. So I know it sounds a little counterintuitive to be like, well, why do I care about this angle when both of these angles are 45 degrees? So remember, whenever you're setting up the trig ratios, you always have to have an angle of reference so that you can label the different sides of the triangle. So since I'm always interested in the angle that is close to the origin, that makes this side of my triangle adjacent, and that makes this side of my triangle opposite. Now that I have my special right triangle and I've also labeled all of the sides based off of the angle of reference, and I know what all the side lengths are equal to, I can start setting up my 6 trig ratios. So remember, sine is always equal to opposite over hypotenuse. So this is going to be the square root of 2 over 2 over 1. My cosine is always equal to adjacent over hypotenuse. So this is going to be square root of 2 over 2 over 1. And then tangent is always equal to opposite over adjacent, which is the square root of 2 over 2 over the square root of 2 over 2. So I went ahead and cleaned all of these up. So you get the square root of 2 over 2 is equal to sine. You get the square root of 2 over 2 is equal to cosine, and you get tangent is equal to 1. So this should make some sense because since we have a 45, 45, 90 right triangle, that means 2 of our sides are going to be the same, which is why we got 2 of the same trig ratios. So remember that the other 3 trig ratios are the inverse of sine, cosine, and tangent. So I'm not going to solve for those in this video because we should know how to find the inverse of trig functions. But I want you to use everything I covered in this video to complete your packet. So good luck and try your best.